This is fourth lecture of module 3. We will continue with the solution of linear system of equation. In the last lecture, we have seen Gaussian elimination, LDLE decomposition, and previous to that we have also seen Gauss-Jordan elimination. So, in this class or in this lecture, we will learn Chomsky decomposition. Chomsky decomposition is one of the important factorization, matrix factorization scheme which we will be using, and then we will see some of the partitioning advantage of matrix partitioning. So, before doing the Chomsky decomposition, let us know one type of matrix which in the structural system we always observe. So, that matrix is called positive definite matrices. Now, a real symmetric matrix A to be positive definite if and only if following conditions are satisfied. For instance, the matrix has to be for any non-zero vectors of x, the x transpose A x is a scalar and which always should be greater than 0. All eigenvalues of A must satisfy greater than 0 condition. That means, all lambda i's, if lambdas are eigenvalues, then all lambda i's should be greater than 0. Then all upper left submatrices A k have positive determinants. So, this I will explain. Eigenvalues we are not discussing in this course, but I hope that all of you have an idea of what is eigenvalue. And then the last point which we have already learned in the last class is that all pivots without row exchange are greater than 0. So, now, so the first condition is essentially the non-zero for all non-zero vectors x transpose A x, which is a scalar, has to be 0. The second condition is the eigenvalue condition, and the third condition is the upper left submatrices A k have positive determinants. So, the first condition, there is an example, let us say A, B, C are vector, so which is non-zero vector. So, if I transpose that vector and multiply with a matrix which is A is and then again multiply with that vector, then we obtain something like this. Now, this scalar, this is a scalar. So, all are, you see that all quantities are positive, because this is a square. So, this cannot be negative, this is also a square, this cannot be negative, and C is squared, this cannot be negative. So, this proves the first condition that all for any non-zero vector will obtain a scalar x transpose A x, which has to be greater than 0 for positive definite matrices. Now, second condition is that eigenvalue condition, all eigenvalues has to be greater than 0. So, if you find out eigenvalue of this matrix A, then you will see all eigenvalues are greater than 0. And the third condition, for instance, the all upper left submatrices A k have positive determinants. What does this mean? So, the first upper left submatrix is actually the first element of that matrix. So, this is actually 2, which is greater than 0. So, the second upper left that matrix is actually this matrix. So, if you consider the determinant of this matrix, so which is 2 into 2 minus of minus 1. So, 3. So, this is the this is again greater than 0. Now, the third upper left, since the matrix order is n, so this constitute the determinant of A. So, if you compute the determinant of matrix A, which will be greater than 0. So, in a, what does this third condition means? So, if I draw a matrix, so this is the first upper left matrix, then the second upper left matrix is this, and the third upper left matrix is this. So, this is the first element of the matrix, then this is second element, and then the whole element of the matrix for which the determinant has to be 0. So, it can be generalized for n cross n positive definite matrices. So, in that cases there are n such determinants we can find out, and all such determinants has to be greater than 0. So, this is actually the positive definite matrix, and in a structural system we will actually obtain this positive definite matrices very often. So, because symmetric matrices we will also see these matrices are symmetric, because for instance in a reciprocal theorem you have learned in your that structural analysis course, which sometimes results in symmetric stiffness matrices, and those matrices has to be the positive definite. So, we will see when we discuss beams and trusses and frames. So, now if the matrix is symmetric and positive definite, then what is the how we can compute its solution. So, for instance, there is one factorization known as Chomsky factorization. So, let us see what is this. So, let A be a real symmetric and positive definite matrix. So, there exists a unique real lower triangular matrix L having positive diagonal entries such that A can be written as L transpose. So, this is L lower triangular matrix. L is the lower triangular matrix. We know what is lower triangular matrix, and so obviously L transpose will be the upper triangular matrix. Now, if we can decompose a matrix in this form, then obviously its determinant is one of the matrices square. So, so this type of decomposition is known as symmetric Chomsky factorization, which is valid for positive definite, symmetric and positive definite matrices. Now, we will see how we can do such decomposition. So, as we have learned in the previous slide that a positive definite matrix should also satisfy x transpose A x should be greater than 0, and for your information, this quantity is often known as quadratic form. So, even though we will not use this in this course, but it is better to know this. So, now how to solve such positive definite matrices, or how to solve such positive definite system of equation where the coefficient matrix is positive definite. Let us see. So, as per our definition, a matrix can be decomposed into two such things like LU decomposition we have learned in the last lecture. So, here instead of the matrix U, which is the transpose of L, the lower triangular matrix. So, if we do such things, then by the matrix multiplication we can easily get the final form of the matrix. So, now from here, by comparing the each element of the matrix, we can find out what is the L11, L21, L22 and so on. So, let us see how it takes this L21 and the Lij's, how it takes. So, if we do this, then it turns out that L11 is root over of A11. So, the first important thing is that A11 has to be to find out the LI's or L, the component of the lower triangular matrix, you have to take the square roots. So, this is important difference from what we have learned in the LU decomposition. So, similarly, if I want to compute L21, which is sequential, once you find out L11, then A12 by L, this has to be the L21 or A12, because this is a symmetric matrix. So, this has to be the L21. So, now this L21 can be found out by L dividing by A21 divided by L11. Similarly, L31 can be found out by A31 by L11, and again once we calculate L22, this is again this we have to take the square root. So, this can be observed from the multiplication and comparing the matrices. So, the important information here is that once we perform the Chomsky decomposition, we have to take the square root of the entries. So, now certainly if this quantity, this A11 and these quantities, if you look carefully, are not greater than 0, you cannot take the square root, because it will be negative and the square root will be imaginary. So, which is not our requirement. So, the Chomsky decomposition obviously will fail if these quantities comes as negative. For instance, the first element, which is negative A11. So, this A11 we cannot take square root if we take the negative, if the element is negative. Now, if we do such things, then for n cross n matrix we can generalize it. So, which is as similar to the LU decomposition. We have seen the generalization of LU decomposition. So, the formula turns out to be like this. So, once we compute the L's, the solution is pretty similar with the LU decomposition. So, here Ax can be written as LL transpose X, and as we have assumed that in LU decomposition L transpose X equals to Y and Ly equals to B, and then we first do the forward substitution to compute Y, and then back substitution to compute the X. So, this is the overall procedure for the Chomsky decomposition. But now we will see a modification of this Chomsky decomposition, or the more general form of the Chomsky decomposition, where it is known as an alternative form, also known as an alternative form. This is known as LDLE decomposition. This is more general decomposition, and actually you need not to find out the square root of any element. This has a specific advantage also, that matrix need not be strictly positive definite. So, in case of a positive semi-definite matrix, this procedure can be applied, and which is pretty general. We will show with an example also. For instance, this what we do is that instead of putting a diagonal element some value, we restrict the diagonal element of the lower triangular matrix L is 1. So, the upper triangular L transpose will also be diagonal element will 1. But instead of multiplying L transpose, we multiply L D, which is again a diagonal matrix, and L transpose. So, if a matrix can be written in this form, L D L transpose, then again we can find out the L ij's and D ii's. So, by comparing each element of the matrix. So, let us see, for instance, this if A is an n cross n matrix, then this comes out to be the general formula for L and DII, Lij and DII's. So, as we have seen in Chomsky decomposition, that we need to for the diagonal element of the rectangular matrix we need to perform the square root. Here we can avoid that square root. So, this is relaxation of the strict condition of positive definiteness of the coefficient matrix, which can be symmetric indefinite form. So, we can see with an example what does this means. Now, once we have the decomposition, the solution or the finding out the x is very similar, which is Ax equals to LDL transpose y. So, if you assume that L transpose x is y, then again we have to assume, because we have a 3 matrix here. So, D is also assume dy equals to z, and then Lz equals to b, which finally gives the solution of x. Now, we will see how with an example between these two factorization. Now, let us see, let us take a matrix which is a 3 cross 3 matrix, and this matrix is a we will do it with the Chomsky decomposition. We will factor it with the Chomsky decomposition and LDL. Now, the first term, as we have seen in the last slides, that L11 is root over A11, which is okay because A11 is positive. So, we can take the square root. Similarly, we can find out the L21 and L31. So, that is fine, which is okay, because these divisions, if as long as L11 is non-zero, so this division works fine. Now, L22, when we calculate L22, which we have seen from the Chomsky method, is that A22 minus L21 square. So, now, L21 we have found out 3. Now, A22 is actually 1. So, 1 minus 3 square is root over minus 8. So, here you can see that Chomsky method fails. So, this matrix, even though it is symmetric, but it is not positive definite. Why? The reason is we can quickly see what is the reason. For instance, if you remember the third condition of positive definite test, that all left upper left submatrices, the determinant of all left upper submatrices has to be greater than 0. So, if you now test that, so if that first upper matrices is the first component of the matrix, which is 1, and the one determinant of 1 or the scalar is 1 itself. So, it is greater than 0. Now, if you see the second upper left submatrices, which is this, which has to be greater than 0. Now, if you take this portion, if you see the determinant of 1, 3, 3, 1, you will see that the determinant is negative, and which is actually the minus 8. So, that is why this matrix cannot be said as positive definite, but very interestingly, the determinant of this matrix is positive. So, if you compute the determinant of the whole matrix, which is a 3 cross 3 matrix, it is positive. But the second upper left submatrices, or this matrix 1, 3, 3, 1, which is not the determinant of which is not positive. So, Chomsky method will fail. But on the contrary, if we use LDL transform or LDL decomposition, so the diagonal element first we calculate, which is D11 is 1. Then again we calculate L21, which is A21 by D11, which is 3, and then L31 is A31 by D11, which is again 4. Similarly, we calculate D22, which is A22 and L21 square D11, which is minus 8. You see, since there is no square root, it does not fail here. So, similarly we can find out L32, and similarly we can find out D33. So, the decomposition works here, LDL decomposition works even though matrix is not strictly positive definite, or we can say the matrix is positive semi indefinite. So, now the advantage of LU decomposition is that even though LU decomposition is valid for general matrices, we will mostly use the symmetric matrices and mostly use the symmetric positive definite matrices. But what may happen is that in all numerical computation, for instance, the determinant when you calculate, when you have a large matrix A where all entries are different order. For instance, one of the entries is 10 to the power 4, one of the entries is 10 to the power minus 8. So, rounding of error and all those things occur in the numerical computation. So, the determinant which we compute in a computer code may be nearly singular or maybe very not greater than 0 sometimes. So, in that case we may have to use the LDL transform, LDL decomposition method to solve the problem. Now, this we'll see when we will learn for the structural systems. So, now there is another important thing here we need to know is that the matrix multiplication by partitioning or the matrix partitioning. Suppose you want to multiply a 1000 cross 1000 matrix with another 1000 cross 1000 matrix. So, first in a computer code what you generally do is that you store that 1000 cross 1000 matrix and then multiply it. But this is not only a very huge memory will be allocated in the computer and your process could be slow due to that. But there is a way of doing that. If you partition this matrix in such a form that say this is a 4 cross 4 matrix and we partition with a 2 cross 2 form. So, this is the partition matrix. We partition this matrix and this block matrices A11, A12, A22, A21 and 22 we write in this block format. And then this is also another 4 cross 6 matrix and we want to multiply 4 cross 4 with the 4 cross 6 matrix. So, if we partition it again, it is 2 cross 3 at each block matrix. So, B11, B12 and B21, B22 we can write. Now, this is A11 and B11 we can see. Now, if we want to multiply this two matrices A and B which is a 4 cross 4 and 4 cross 6 matrix. So, we could use the partitioning algorithm or matrix partitioning method to do the multiplication efficiently. For instance, here we multiply. So, since A is a 4 cross 4 matrix and B is a 4 cross 4 matrix, its multiplication will result in a 4 cross 6 matrix. So, if we multiply A and B together with the partitioned block matrix form, then if we write it, it is A11 B1, A12 B21 and so on. So, this form, if you see importantly, this is actually the multiplication of A11 is 2 cross 2, A11 is 2 cross 2 and B11 is again 2 cross 3. So, similarly A12 is also here 2 cross 2 and B21 is 2 cross 3. So, in this way we can reduce the storage of the matrix. So, this is the general formula if you want to write it in a general format. So, if there is a number of partitions if you decide, and then its multiplication will look like this. Now, this has a clear advantage in our this course, which we will see through an example. Let us see what is that. So, suppose we want to solve this matrix system of equation. Now, here what happens is that my x1 and x2 are unknown and x3 and x4 are unknown. This kind of situation occurs when we see what is the stiffness method, where the x1 and x2 are the unknown displacements and x3 and x4 are unknown forces. So, corresponding to these unknown displacement, we have 5 is the force and x2 is the 10 corresponding to that force is 10. So, now this x3 and x4 is the unknown force where we know the displacement. For instance, the boundary condition, the cantilever beam, you have the boundary condition is known at the fixed end, it is displacement and rotations are 0, but you do not know what is the moment due to the applied load and shear force. So, this kind of situation as we may observe in matrix method. For instance, this matrix could be a stiffness matrix K, and this matrix is a delta, and this matrix is a force matrix. So, this such situation, in such a situation we have partial delta known and partial F known. So, what we need to do is that we need to first find out the unknown deltas with the known F's, and then use that solution to find out the unknown F's. In such cases, the partitioning, matrix partitioning is very helpful. For instance, here we, as per the unknown deltas, we partition this matrix in again 2 cross 2 form and then write it in this form. So, A11 and A12, A21 and A22 is Y1 and Y2. So, Y1 is essentially x1 x2 and Y2 is essentially 1 2 vector. So, now similarly the force matrix or force vector we can also partition, so which is B1 and B2, and B1 is essentially is your 5 and 10, which is a known vector, but B2 which is unknown for us. So, now if we write this system of equation in the block format, so it is A11 Y1 and A12 Y2 and B1 and A21 Y1 and A22 Y2 equals to B2. Now, here you see the Y1 is unknown for me and B2 is unknown for me. We know Y2 and B1. So, from the first equation we can calculate Y1 which is A11 Y1 B1 and A12 Y2, because since we know Y2 we can multiply with the coefficient block matrix A12 and then subtract it from B1, which will give me the right hand side of this system of equation, and then we can find out Y1. And similarly, once we know the Y1, that means we know the unknown displacements, and then we want to compute the unknown forces, which is B2. So, again A21 Y1, since we have found out Y1, A22 Y2 and Y2 is known to me because Y2 comes from the boundary condition of the problem. So, if you do this, then we can find out the B2, the unknown displacement. So, similarly, in this example, this first block matrices is A11 is multiplied with the x1 x2, and which will give me the modified right hand side, which is 5 10 minus this second block matrix, which is A 1 2 and then the known displacement vector, which comes from the boundary condition, and this is the B1. So, once we do that, we get the modified right hand side, and we can use any of the decomposition methods we have learned, or any of the solution system, solution of linear equation, any of the method for solving linear system of equation we can use to find out x1 and x2. So, once we know the x1 and x2, then the force vector, which is unknown at the known boundary condition n, we can find out x3 by x3 and x4, which is again the block matrices A21 and using A21 and A22, which is actually the y1 here and this is the y2. So, we substitute known x1 and x2 from the previous equation in this equation, and then we just do the matrix multiplication to find out the unknown force vector. So, this technique is worth remembering because we will be using this technique or in this course, and this is how we actually implement the boundary condition in the system matrix or the stiffness matrix. So, when we will learn specific problems or specific structural type, we will use this kind of partitioning to solve our system or finding out the unknown displacements. So, that is all. So, in the next class we will learn what is matrix rank and its linear independence. Thank you.